Hello everyone. Welcome to week 9 live session of NPTEL's Introduction to Semiconductor Devices course. I am Om Maheshwari and today we'll be doing some problems that will help you with your assignment as well as your exams. So let us start. In this week, mainly we will be discussing about long channel MOSFETs. So this is one of the most important topic of this course. So I suggest you to please watch the videos very carefully and also follow the reference books if possible. I'll quickly review the slides from Professor Naresh. So this is the MOSFET device. Till now, we were for the past 2-3 weeks, we were studying MOSCAP. That was just this part. Now we have a source as well as a drain. So now it is a 4-terminal device. We have source, drain, gate, and body. So the current can flow from drain to source. This is just a layout or the top view of this MOSFET. So this is the gate, this is source, and this is drain. This is the top view. This is the 3D figure for the same. Okay, so in MOSFET region of operation, the mode of operation is very similar to MOSCAP. There is nothing much different. If you see, uh, it again has subthreshold and beyond threshold regions with the uh, accumulation, depletion, and inversion regions. So the operation is pretty similar, just that you have an additional control now on these two terminals, source to drain. So once you have formed a channel, you can give a potential difference here to allow the current for allowing the electrons or the holes to flow. So once the channel or the inversion layer is formed, you can give a potential difference between these two terminals to allow the flow of electrons or holes. So, so when the gate voltage is less than threshold voltage, that is the channel is not, uh, sorry, when the gate voltage is greater than threshold voltage, then the channel is formed, that is the MOSFET is on. In that case, when you apply a small voltage, let's say, so it is operates in a linear region and yeah. Mm. Okay, so this is the current equation in the linear region, which you might have seen earlier also. So here from this ID VDS graph, how current is changing with drain voltage, you can see all this part is linear and all this part is saturation. In saturation, the current has become constant. So why this happens, that you would have, if you remember from the lectures, it's due to this pinch off condition. When your VDS is greater than or equal to VGS minus VT, then saturation occurs and the charge here it becomes zero. So this is condition is called pinch off. So when it is pinched off, your current starts to saturate. And when you keep on increasing VDS more than VGS minus VT, this pinch off point shifts towards left, like till here. Earlier it was here, now it will be here. So okay, this was about pinch off. Then in saturation, there is no VDS dependence. In saturation, the current is this mu Cox W by 2L VGS minus VT whole square is the value of current that is not dependent on VDS in saturation. It is constant, but it is quadratically dependent on VGS minus VT. Now the body effect, so you have body terminal also. If I draw the band diagram by taking cut line here, this is source, gate and drain. So this is source, gate and drain. So for electrons to go from source to drain, you apply a positive Vg here to lower its this barrier, so electrons go, right? That's how your electrons come from source and drain in the MOSFET to form the channel. Now, if you are applying a body potential also, so let's say you apply a positive VB, what will happen is this positive VB will can also forward bias and it will bring more electrons here. So this VB will lower your threshold voltage. So this dependence of VB on threshold voltage is taken care by this relation. VT is VT naught plus gamma under root 2 phi f minus VBS minus 2 root phi f. And this is body effect parameter. So this body effect parameter is given by 2q epsilon si Na by Cox. This is your body effect parameter. Now the question is, what is a good MOSFET? So, okay. So in good MOSFET, it should follow all the ideal relations that we have studied. Like it should be linear in this linear region. It should be behave like a constant current source in the saturation region. It should not increase its current in the saturation region. Further, if we right, so this should not happen. Right, in this ID VDS, it should be constant in this region. So this is changing because this output condition in this output curve ID versus VDS. So in this output curve, ideally this resistance here should be infinity. The output resistance should be infinity. So this conductance should be very small. And in digital applications, MOSFET is used generally as a switch, right? So drain source are always connected in the circuit. Gate is like acting a switch. If you apply VG greater than VT, your this path is formed and the circuit turns on. If VG is less than VT, this switches off. So how you want ideally this circuit to behave is like it should behave like this, right? If it is on, it should be high. If it is off, it should be low. But this is the MOSFET behavior. So we want this slope to be as high as possible. We want it to be like this, like a switch, right? We want it to instantaneously go from 0 to 1. So we want the slope to be as high as possible. So this is quantified with help of subthreshold swing factor. Subthreshold swing tells us how ID current changes with respect to gate voltage. So we want a large current change. Current should change like this in a very small voltage change, right? So, but this still has some physical limits. So by definition, the this subthreshold swing uh, is formulated as this nkt by q into 2.303, and this n minimum n is 1. It cannot be lower than 1. So this comes out to be 60 millivolt per decade. What it means is for one decade change in a current from, let's say, from 10 to the power minus 7 to 10 to the power minus 6, you need minimum 60 millivolt voltage change. This is the theoretical limit at 300 Kelvin temperature. So this is a CMOS inverter. Now we have PMOS and NMOS stacked together. So when input is 0, this NMOS will be off because gate voltage is 0, but PMOS will be on. So your output will be VDD. When input is 1, your PMOS will be off, NMOS will be on, and output is ground. This will be shorted here. Okay, so this was a very quick revision of the slides, but I highly recommend that you watch the video lectures as well as read the uh, books. So, okay, now we can start with questions maybe first. Concept of edge of saturation. There's nothing like edge of saturation. It just means like, yeah. So this condition is called as edge of saturation, right? When VDS is equals to VGS minus VT. This is like the edge of saturation. You need this minimum VDS to have the transistor in saturation. And what happens here is you're at this particular uh, voltage, your your channel tapers like this. So at the drain end, when you have applied VGS minus VT, what happens is your charge in the channel becomes zero. Okay, so why this happens is your inversion charge. Q inversion is Cox VGS minus VT minus VDS. Now, if you if VDS is also equal to VGS minus VT, the Q in will become zero. If VDS is VGS minus VT, right? So that is what is happening here. This is called pinch off. Now, since this charge is becoming zero, your profile current saturates like this. Is this clear? Okay. So please attempt this question. Okay, so for this question, option A is correct. So in a P-type MOSFET, this is source, this is drain, this is gate. So for P-type MOSFET, you should have VSG, okay, or VGS should be greater than or equal to VT, right? And VT is always negative. So what you can have is VSG then equal to mod VT. So generally we have this is VDD, this has some lower voltage. So VSG is VDD, then your transistor turns on. So it is option A. Next question. Consider an N-channel MOSFET with following parameters. The drain current ID for VGS is zero point 0.4 and VDS is 1.2 volt is what? Please note this Kn is mu and Cox. Try to find the answer.
धर्मेंद्र जरा देखो क्या हुआ.
Okay, so let's see this one. So we have ID. Okay, so
I'm really happy for you that the artist retreat plan is coming together. I really, but right now.
so we have VGS minus VT is 0.4 volts and VDS is 1.2 volts. So what this means is VDS is greater than VGS minus VT. That means it is saturation. Now in saturation, the current is mu n C ox W by 2L VGS minus VT whole square. This mu n C ox is 0.18. W by L is 8 by 2.4 square. Solve this. ID is okay. So answer is option B. So yeah, so this is, you need to remember this 2 is there in the denominator in the saturation current equation. So this is a very common mistake which you should avoid. Next one. For a long channel MOSFET biased beyond pinch off, the saturated drain current varies as right. It is this option. We just saw ID is mu n C ox W by 2L VGS minus VT whole square. So this is whole square term is there after saturation. Okay, next question. Okay, so the answer to this question is option B, increase in gate voltage required necessary to increase the drain current by factor of 10. This is, we measure the substantial swing in log ID versus VGS graph. Looks like this. We measure in this delta V how much this delta V is required to change the current by a factor of 10. So SS is delta V by log ID2 minus log ID1. So this is ID2, ID1. It's option B. The material shows drain current. What do you mean? Yeah, so this is gate voltage. This is drain current. Okay, next question. What is the minimum subthreshold swing of a classical MOSFET at T equals to 300 Kelvin? Right, it is 60 millivolt per decade. Okay, and if you want to see how where it comes out, it is N KT by Q to 2.303. So the minimum value of this N is 1 at T equals to 300. This is 1026. So SS is, which comes out to be, which is 60 millivolt per decade. Okay, next question. Okay, so the question is the transfer characteristics for an N-channel MOSFET is given. Identify the mode of operation in the regions A, B, and C. So region A, we are going lower in the VGS, right? That means it could go below subthreshold. Region B and C are transition from VDS by region B is linear and C is saturation. So A, B, and C should be subthreshold, linear, and saturation. Option C. Next question. In a MOSFET operating in the saturation region, the channel length modulation effect causes what? Okay, so what channel length modulation does is, so you have seen this in the output characteristics. So in the saturation region, Ideally, we want the current to not change with VDS, but due to channel length modulation, there is this change in current. So what we want is del IDS by del VDS to be high. So, but here del IDS by del VDS increases due to CLM, channel length modulation, which in turn, this means the output conductance increases or output resistance decreases. So it is option B, a decrease in output resistance. Okay, next one. Consider an N-channel MOSFET with following parameters: conductance parameter, threshold voltage. What is the drain current for the following gate voltage and drain voltage? So here one thing to note, this conduction parameter. This is mu n Cox W by L. So try to solve this. Okay, so ID is okay. For finding ID, VTH is 0.75. So VGS minus VTH is 0.75. VDS is 1 volt. So VDS is greater than VGS minus VT. That means it is saturation. Saturation ID is mu n C ox W by 2L VGS minus VT whole square, which is 1 into 1 by 2 into 0.75 square. This is 0.28125 milliampere. This is option A. Okay, next question. Consider an N-channel MOSFET with threshold voltage VTH operating under pinch-off condition. Choose the correct condition that indicates the onset of pinch-off. So onset of pinch-off means onset of saturation. So the onset of saturation is VDS greater than equal to VGS minus VT. When it starts is VDS equals to VGS minus VT. So it is option C. Next. Okay. For short channel MOSFET with P-type silicon substrate, the critical field at which electron saturation occurs is around 1.5 volts per micrometer, and the saturation velocity V set is 10 to the power 5. Based on the figure below depicting the saturation effect, choose the incorrect statement. Options are: for lower field strength, carrier mobility is not constant. The slope of region before reaching critical electric field strength EC represents carrier mobility. The velocity of the carrier tends to saturate due to scattering effects. Velocity saturation effects are less pronounced in PMOS. Okay, so the answer is option A. So A is incorrect. Rest are correct. You have to choose the incorrect statement. So this is um, quite obvious here. So here in this region, we see here V is proportional to E, right? And it is linear. So the constant would be V equals to mu E. This is we have seen in first class itself, first or second class, right? So you should remember your basics. VD is mu E, right? This relation, and this is velocity saturation. We have also seen already. So here in this region, mu is constant. V and E are linearly varying, mu is constant. So for lower field strengths, carrier mobility is not constant. This is incorrect. Option C is correct itself. So this saturation happens because of scattering only. At very high electric field, there is optical phonon scattering due to which this saturation occurs. Next question. A silicon MOSFET has following parameters. The body coefficient is what? So what is body coefficient? Gamma is 2q epsilon Na by Cox. So use this formula and try to solve it. Okay, so let's try to solve this. Under root 2 into 1.6 into 10 to the power minus 19. Epsilon silicon will be 11.7 into 0.854 into 10 to the power minus 14 into the power 16 divided by Cox. Cox is epsilon ox by Tox. Epsilon ox is 3.9, 8.854 into 10 to the power minus 14, and Tox is 12 into 10 to the power minus 7. So if you solve this, you get 0.2 root volt. So it is option B. Please check your calculations if you are getting something else. Next one. What is the main function of P channel MOSFET in a CMOS inverter circuit? You used M. What is M? But that still does not change the answer. Answer is in this unit, right? There's no meter or centimeter here, it's just volts. So if you have to use meter units, you have to change all of these in meter units. You cannot just change this and expect the answer. Okay. Next question. What is the main function of P-channel MOSFET in a CMOS inverter circuit? So if we have a CMOS inverter circuit, so here we have input, this is output, this is VDD, this is ground, this is PMOS, and this is NMOS. This is a CMOS inverter circuit. What is the function of this PMOS transistor? It is to pull the output to ground when input is high, to provide constant current source, to pull the output to VDD when input is low, to invert the signal. Okay, so let's think about it. Let's say when V in equals to 1, V out must be 0, right? This is how inverter works. Now when V in is 1, since this is already VDD, this transistor PMOS will be off, NMOS will be on. So this is the path which is shorted, which is connected to ground, which is connecting output to ground. So that's because of this NMOS, your output is ground. When V in is 0, V out will be 1. So when V in is 0, NMOS will be off, PMOS will be on, and this path will be shorted. So this VDD will be connected to output. So the answer is to pull the output to VDD when input is low. So it is option C. Because when input is low or input is 0, then only PMOS will turn on. Rest all are incorrect. A is incorrect because this is the job of NMOS. Provide constant current, so this is not needed. Invert the signal. Inversion is because of both of these, right? Not just because of PMOS or NMOS. Okay. Yes. NMOS provides the path to ground. When Vin is 1. When Vin is 1, this will turn on, this will be off, and this will be connected to ground. Please read the question again. What is the main function of P-channel MOSFET? What is the function of PMOS is asked in question. The function of PMOS is to pull the output to VDD when input is low. When input is 0, PMOS will turn on and pull the output to VDD. Next question. The ideal long channel NMOS and PMOS devices are shown in the circuit, which have threshold voltages of 1 volt and minus 1 volt. The MOSFET substrates are connected to the respective sources. Ignore any leakage and capacitors are initially discharged. For the applied voltages, what are the steady state voltages? So we have an NMOS and a PMOS. Let's first consider NMOS. So here you have applied 5 volt here, 5 volt here, and some V1 is here. Okay, so when NMOS is on, it should directly pass this 5 volt, right? But for it to be on, VGS should be greater than VT, right? And VT is 1 volt. So so here if this is source, this will not happen. So this must be the source, then only this VGS can maintain some difference, because here VGS is 0 if this is source. So this must be drain, this is source. This is drain, this is source, this is gate. So VG minus VS greater than VT. So 5 minus Vs is greater than equal to 1. So Vs should be greater than equal to 1 volt. This Vs is V1. Sorry, greater than equal to 4 volt. So V1 must be 4 volt. So with this only we can see answer is option C. We can also see in PMOS. In PMOS, what is there is minus 5 volt here, 5 volt here, and V2 here. So for PMOS, VSG should be greater than equal to mod VT. So here VSG would be 10 volt, which is greater than equal to mod of minus 1. So it will be on. So this 5 volt will directly pass here. So V2 will be 5 volt. So answer is option C. V1 is 4 volt, V2 is 5 volt. Next. So this is the last question for today. The question is, an NMOS transistor operating in linear region has this much current and VDS of 0.1. Keeping constant VDS is increased to 1.5 volt. Then what is the transconductance at the new operating point? Please attempt this for a minute, then we'll solve it. So let's see this. We know first for linear region, ID is UNC ox W by L VGS minus VT into VDS minus VDS square by 2. So 5 microampere is 50 microampere per volt square to VGS minus VT into zero point 0.1 minus zero point 0.1 square by 2. So if we take zero point 0.1 common, and this will be, we take zero point 0.1 common from here and here. So 50 into 0 0.1 will be 5 microampere. This 5 and 5 will cancel. So we will have 5 by 5 will be VGS minus VT minus zero point 0.1 by 2, which is 0.05. So this is 1. So VGS minus VT will be 1.005 volts. Next, now VDS new is 1.5 volt, so which is greater than VGS minus VT. Now it is in saturation. So in saturation, ID is mu and C ox W by 2L VGS minus VT whole square, and GM is del ID by del VGS. If we differentiate this ID with respect to VGS, we get is mu and C ox W by L VGS minus VT, which is 50 microampere per volt square into 1.05. This is, in solving, we get GM equals to 52.5 microampere per volt square. Sorry, per volt. So answer is option C. Okay, so these are all the questions that I had for today. If there are no more doubts, we can close this session. The next class I will take on is on this Sunday, where we'll see week 10 questions. So thank you for joining. I'll see we will meet again on this Sunday. Please feel free to email me if you have any doubts. Bye.